3, and what I thought I would do is go over problem number 7 with you. I thought this would be a good review for exam number 1. So you see a couple of resistors here that are in parallel, and you got another pair of resistors that are in parallel here. And remember, the way that you add those is, well, not add them, but you find the equivalent resistance by taking the sum of the reciprocals over the reciprocal, and for this one, for the 50 and the 100, I get 33.3. Doing the same thing for the pair of these resistors up here, 25 and 75, I get 18.75. So this arrow right here just means equivalent circuit. I keep going down one more, and I see that these two are in series, so I replace that with the sum of 18.75 plus 33.3. And there's my equivalent resistance. So if I had an ohm meter between these two without that power supply there, I'd read 52.1 with this resistor or with that pair, or if I had all four of these and I didn't have the power supply there, just an ohm meter, I would again read 52.1 for those four, for these two, or for that one. So that's what we mean by equivalent resistance. Now what it's saying here is that you have a 12 volt power supply, so I've applied that across the terminals like this. And if you start at the bottom, what you can do with that is find the current that is supplied by the 12 volt power supply. So I'll call that I sub S for the current supplied by the source. Now this is in series with this equivalent resistor here, so that means that I sub S is not only being supplied by the power supply, but also it's the one going through the equivalent resistor. So if I use Ohm's law, I can say that the current being supplied by the battery is the 12 volts divided by the equivalent resistance, or 0.23 amps. Now, if I use this V sub T and V sub R to represent the voltage drop across the top resistor and the right resistor, that's the T and the R, then what I can do is, since these are all three of these components are in series, the source, the resistor, and resistor are all in series, that means that the current is the same through all of those components. That means that it's still the 0.23 amps going to the middle equivalent resistance. So if I use the 0.23 amps times the equivalent resistance of the top leg, remember that that was 33.3, that tells me the voltage drop across the top branch here, this part right here. Doing the same thing for the rightmost, I use the 0.23, because again it's in series, times the equivalent resistance of that side part right there, 18.75, and I get 4.33. You might notice that if you add those two together, you're going to get 12 volts, which it should. So you have a rise of 12, a drop of those two, and they should add up to 12 volts as well. Now, what you realize in going from this middle step up here is that these are in parallel, so they should have the same voltage drop across them. In fact, they're going to have the same voltage drop across them as this equivalent resistor as well, just because of the parallel property here. If you have components in parallel, they're going to have the same voltage across them. And I got this one labeled R1 and R2, so that means that if I'm looking, as it says right there, find the voltage drop across each component. If I'm looking for voltage across 1 and 2, it's equivalent to the voltage of the top one for my middle branch here, 7.67 V3 V4 equal to the voltage drop on the rightmost branch. And so that's how you break down the problem. You can find the equivalent resistance, then use that to find the current from the source, and then work your way back up to find the voltage drop across every component.